Okay. Okay, so we are now recording on the cloud. Okay. Yes, the one that are online, please. If, I mean, keep it mute unless you want to ask questions at the end. That in that case you can unmute and also show your face in the camera. Okay. So well, it's a pleasure to introduce Massimiliano Luca, that is a PhD student from the FBK. No, even though you are in Bolzano officially, get localized a little between Bolzano and Trento. FBK is a Fundación Bruno Kessler that is in Trento, and actually we know some people from there now. Okay, because some of them were there, our students and former postdocs. Okay, so well, I mean, he has been working on the use of machine learning in mobility, and that's a very interesting work. So he will talk about that. Okay. Well, Massimiliano, the floor is yours.
Yeah. Okay. Thank you so much, and thank you everyone for being here, and also you online. So and thank you for the introduction. So today we are going to talk a bit about deep learning models for human mobility, and in particular new challenges. So basically having something that can be geographically transferable, and we're also going to see what does it mean. So let's get started with a bit of introduction and why it is important to study human mobility. Well, the United Nations some years ago set out a lot of goals for sustainable development that actually summarize the challenges that we have in our society nowadays. And many of them, so thus, for example, are extremely related to human mobility in some senses, right? And to solve some of them, maybe collective mobility, study collective mobility is necessary. So, for example, flow of people and how many people go from an area to another. And this can be the example of health, for example. So we saw also with the diffusion of COVID the importance of having information about the flow of people between locations. And others, so for example, inequalities. So there is a recent work by Esteban Moro that showed that individual mobility can actually help to understand how inequalities are developed within a city and how we can eventually reduce them, right? And at the moment, what we have is that there is this need in the society that is summarized over there. So there is this social pool in some sense, right? And on the other end, actually, there are deep learning techniques that are evolving, that are more powerful than before, and actually have to play a role in solving such problem. And this field is called computational sustainability. And many works of human mobility can actually be linked to computational sustainability, right? So how can we investigate human mobility and try to solve such challenges? Well, with data, of course, and there are two kinds of mobility that we're going to focus on. So the individual mobility, so trajectories in other terms, where basically we want to understand how a person, so a specific individual, move around a city or around an area, okay? So we have a trajectory of a user, which are spatiotemporal points with a location that can be the identifier, okay, of a point of interest, for example, or even the latitude and the longitude, and the temporal aspect. So we know when this guy visited the location, right? On the other hand, if you want to investigate collective mobility, we need to talk about origin destination matrices, right? So origin destination matrices are a simple concept. So basically we have areas, for example, A, B, C, D, E, and F here, okay? And we simply want to measure how many people move from A to B, for example. And this is the case of these three, right? So the origin is A, destination is B, and there are three people moving between them. So which data can we use to measure such things? Many, actually. GPS data, for example. So derived from GPS receiver from boats, vehicles, and other things. Also mobile phone data that are usually collected by telco companies, okay, to, well, billing purposes, but we can also understand human mobility with them. Another example are social media data. So for example, when you tag a place in Twitter, like, okay, I'm here and I'm doing this tag, we can retrieve such information and try to derive mobility in some ways. And of course, there are some pros and some cons, okay, in all the cases. We can eventually discuss them later. And there are many data sets actually that are publicly available. So here's a list, for example, and we collected also them recently in a survey that now is in ACM Computing Survey, a journal. But so we have a problem over there. We have many actually open data sets, but most of them are collected in just a couple of areas. So for example, we have many data sets that are collected in New York as a city. So we have taxis, we have bike, we have open data for Foursquare, for example, that is this social media, right? But there are also some other areas in the world when, well, facing such social challenges is very important, but we cannot retrieve such information, and not that easily. Even now that there are more open data, thanks to COVID, okay, because companies started to open a couple of information. And so we have to understand a bit what we can leverage the data that we have in the places that we have, okay, and actually use them to gather some insights. So for example, generate such flow or predicting where a person will go next, okay, even in cases and scenario in which we don't have such information. So for example, just to give you an idea, take the flows of taxis and bikes in New York where we have data, okay, and generate insights, for example, in sub-Saharan countries where we have problems with epidemics, okay, that are studied in many different papers, but maybe data are a bit more scarce. And so the question is whether we can use learning, so new techniques, to create something that is geographically transferable, meaning that I train a model in an area where I have data, and I test and evaluate the model in areas where I do not have such information, okay? So let's start with collective mobility, because it's a bit more simpler, okay, in this sense. So there is this paper that is now in Nature Communication, where we want actually to understand whether we can use deep learning, okay, to generate flow. So flow generation is this task. I have an area, okay, I have some information, and I want to generate realistic mobility flows among different locations. So for example, census areas, census tract, okay, and yeah, with some given property. So how we do it usually? With the gravity model. So the gravity model is as simple as the gravity law, okay, where we assume that flows decay with the distance and grow with respect to the population. We take the Newton's gravity law, basically, and we fit some parameters to understand the role of distance with a decay function, of course, and the population, okay? But actually, well, we can estimate then using maximum likelihood and also other things. And there are some pros and cons. So parameters are for sure easy to fit, and we can reach state-of-art performances. And there are many applications actually that use gravity model. But on the other hand, we may have a problem of underfitting, okay, and low generalization power. And moreover, we have some kind of a poor explanation, right? And many other problems. So for example, when I fix the parameters, okay, such parameters cannot change when I run the model on a test phase, and are basically the same between the areas. That, I mean, it's not optimal in many cases. So we think about such problem, and we found a solution in using deep learning. In particular, deep learning in this case brings us two things that are, let's say, important. That are the deep learning models are able to capture nonlinear relationship between the data. Okay, so they do not assume that there must be a linear relation also with the flows. And also, it is also simpler to put additional information, okay? Because the gravity model, the traditional gravity model, try to find the role of population and distance, okay? But there must be much more, okay? For example, opportunities and reason why I move between areas. That can be, for example, the point of interest that there are in a specific location, like shops or food point of interest and other things. And also we want to use, well, in this paper, explainable AI techniques, so to fully understand the role of each type of location. But so let's take a look at the model. The model is extremely simple, okay? It is not sophisticated, and it does not contain strange things about the deep learning. Let's say this. It's a collection of feed-forward neural networks that are linear layer, okay, in the end with a nonlinearity component attached. And what we want to do is measuring the probability of going from an area to another as a flow, okay? And then, of course, we transfer such probability into a flow using the population information that is available basically worldwide, okay? And again, we push into this model additional information such as the land use, the road network, transportation, food point of interest, and other things. That can be helpful to, let's say, understand why a person may move between such areas. So create some kind of a concept of an opportunity, okay, to move there. So we also have some baseline. Well, the gravity model, we also try to use simply the population and the distance within with the additional insights provided by deep learning. And we also try to put the features, the same features, into the traditional gravity model, okay? Because the gravity model can be also represented with a regression, basically. So we can also feed the data with the additional information. And we evaluate it with the common part of commuters that, I mean, in the end, is simply the similarity between the generated and the real flow. So you can look at it as an accuracy, basically, okay? But let's say that in mobility studies, it is common to use also this common part of commuter. So we collected some information on England, Italy, and New York State, which are basically the output areas, so the regions of interest that we have, okay? And for which we have also information about the population. And those are basically the results. So just by introducing new features and deep learning techniques, you can see that, so those are the observed flow in the first picture, so the A picture. And in the middle, there is the results of the gravity and the traditional gravity model. So you can see that the similarity of this map with this one, so the B and A, is, I mean, greater than the one of C and A. And indeed, we have some relative improvement that go above the 1000% in the case of New York State, okay? And then there may be reason why we have just 50% in Italy and this big improvement in New York. So if you want, we can discuss a bit about it later. But what is more interesting indeed is that actually the relative improvement, so the difference between the central map and the first map, that is again this accuracy, okay, simply shown on a map. So the greatest relative improvement, if you look at map C, is over the cities. So for example, London here, okay, and other big cities here in the north. And we have similar results also in Italy, for example, with Milan and the Turin and the others. And also in New York, well, yeah, where you can see that here, where we have the big city of New York, we have a big relative improvement, and also we have some relative improvement here where there are, well, smaller cities, but still relevant. And those are basically the map that we see before in numbers. So the relative improvement is interesting increase as the decel of the population increase, okay? So meaning that actually, so even if this curve in the first graph decay over the decel of population, indeed, if we measure the relative improvement, which is basically the difference between such lines, the relative improvement increase, okay? And again, also in Italy, and then also in New York, okay? So this is the results for New York, where you can see that, well, differently from before, the performances are more or less stable, but the relative improvement actually increase with on the cities, basically, okay? But so let's say that at the moment we have just yet another model, okay? So there are many models doing this thing, but we also have an explainable AI techniques on the top of the model that can help us in determining what is going on, okay, with the prediction. And so, for example, as you can see here in England, there is in this graph, so the A plot, there is a dot for each pair of origin destinations, so for each pair of potential, let's say, commuting areas, okay? There is the feature that is listed here, and there is this color here, meaning that, for example, this point here, okay, so the red one at the very left of the distance is red, and it means that in that case, the distance was high, okay? So there is a big distance between the two origin and destination areas. And similarly for the blue, we have low values. And the sharp value is nothing more than a number that actually can help us to define the impact of that particular point on the prediction, okay? So for example, we can read it like this. So here I have the red points that tends to be negative, okay? And this means that if I have an high distance, I tend to let's say commute less, okay? And this actually makes sense, because if I have to move let's say far away from for my destination, okay, the flow will be a bit lower, and this makes sense. This is what happened also with the traditional gravity model, okay? But we have also other informations, okay? So for example, commercial end users, we can see that low values of commercial land uses actually, in this case of England, have a positive impact, so augment actually the flows of commuter, and also the opposite. And this is interesting because things, so first of all, there is an important thing here. So we can see that while the gravity model rely on distance and population, here we see that population is not that relevant, okay, because it's sorted by relevance here, in this case, the feature. And also what is interesting is that everything changes, okay, for every single state. So there is not like a constant role of the variables, right? So for example, the distance here is the third, in England was the first one. Here the distance is the second most relevant variables. And here, for example, the population indeed play a crucial role, okay? So, and this can also help policymaker in taking decision and try to understand what's going on. And as far as it is explainable, for example, urban scientists can also use such information to explore what-if scenarios, okay? So think about it, because transportation is basically the third cost that companies are facing in Europe, okay? And so it is very important to optimize transportation, because basically taking less time on the road, taking less time commuting, and also optimize travels among location, okay, is very important. And try to understand how to optimize, for example, the opening of new shops or things like that, or also to place a bus station in a specific place, and having a feedback of this kind can be very important, okay? But so what's happening here? Well, let's skip over this slide. So while we have state-of-art performances, and we also overtake such performances of the deep gravity model, we saw that adding nonlinearity can improve the performance, okay? But also including new variables can play a crucial role and is important, okay? And as we can see, as we saw from the other baselines, okay, we cannot simply just add the nonlinearity to the traditional gravity model or add features to the gravity model, but we have to take the combo of the two. But what is more interesting, in my opinion, is that here about the geographic transferability of the model, it is possible, let's say, to explore such scenario for two main reasons. So first of all, we are trying something, okay, that do not rely on locations, because we rely on distances between location, okay, but it is something that we can compute for every area of the world, okay, and also population, and we have population basically more or less from everywhere, at least estimated. So there are projects like the World Pop project that can give you a projection of the population living in a certain area. But and also point of interest, you can download them from OpenStreetMap, and you can also put additional information such as socio-economic factors, okay? And so we said, okay, let's try if it is true. So because I mean, if everything can be computed and we are not relying on geographic feature, we should be able also to transfer things. And we did it within the UK, okay? So here what you see is the let's say the leave one city out experiment that we run with our model. And so we took the 8 most important cities in the UK, well, and we also took London, that was excluded, no idea why. And basically, so that the red line here that you have, okay, is the result with deep gravity. And the brown line that you have here, okay, is the result with the leave one city out. So leave one city out is this. We take 8 of the 9 cities that we have to train the model, okay? And the third city is basically just a test scenario. So in other terms, we guarantee that we are not observing, for example, in this case here, in the London case, we're not observing any kind of flow in London, okay? and we are just looking at flows in such areas. Okay, and then London is a fully tested dataset. Okay, and you can see that more or less performances do not vary, and in some cases, in London and in Newcastle, for example, and even in Liverpool, performance are increasing. Okay, but in any cases, when performance decreases, such in Bristol and well, and Sheffield, for example, we do not have that that bad performance too. And this is very interesting, but it also has some limitations. So first of all, there must be a way, of course, to represent the geographic features and other things, well, more, let's say, in a more meaningful way. And also we rely on fully connected neural network, which are the very baseline, okay? And we have many studies from computer vision, natural language processing, showing that other things, other deep learning techniques may achieve, better results. But there is something interesting about the geographic transferability. So, because at the moment we are focusing on London, on London itself, on UK, sorry, itself. But we didn't try to actually train the thing, train the model in the UK, and then, for example, test it in Italy, or suppose, test it in Spain. And we may not achieve the same performances, to be honest, because there may be many things, around that can be cultural, for example. So maybe people are traveling in different way. And this is especially relevant if you introduce also a temporal component, right? Because, for example, I don't know, in people in Norway, it's dinner at 5 p.m. Okay, well, here, if you take a temporal component, I mean, you start to have flows toward the restaurants at later in the evening. Okay, and so there may be such things. Okay, this can be potentially, potentially socio-demographic data can also help in transferring such information. Okay, because you start to have more information about the population, so you're not just saying, okay, there are 100 people living in such area, but you may also start to characterize them, okay? And so maybe try to understand a bit more of how people move around and why people move around. That may help in transfer such information. And those are basically two things that, we tried to run, and yeah, then to be honest, we didn't have time to go ahead with the whole experiment and find other insights. But this is definitely a potential interesting path to take, okay, to further test geographic transferability. So what, as you may imagine, actually transfer models, so generative models or whatsoever for flows, it's kind of simple, okay? I have a physical law, nothing related to geography. If I do not want to put them in, okay? It is not the case for individual mobility, as you may imagine, right? Because individual mobility is basically having traces, so trajectory of a person that go in a place, in a very specific place, so location ID, or I don't know, for example, a specific latitude and longitude if you travel by taxi, okay? So it's a bit more tricky, that story. And so what I'm going to present now are some preliminary, there is a paper out on arXiv, but still, let's say it's some kind of a guide again of what we should do to investigate a geographically transferable model. So there is this paper that we submitted to a journal track of a conference a couple of months ago, and can be found on arXiv, when we try to understand whether the next location prediction that are this algorithm that I mentioned. So basically, I have a trajectory and I want to understand where a person will go next, can generalize or not. So can actually be transferred in new scenario or not. Okay. So next location prediction is this. I have information, okay, about a person, or with a user ID, by the way. But I mean, it is not necessary to really associate them to a user. I have a story that can be completed or not, and depending on the data that I have, can also be a bit more sparse. Because, for example, I mean, Twitter data, you have a tweet now and a tweet in 2 weeks, okay. So there are people using it for study human mobility, depending on the area and the user that you take into account may be reliable, more or less, okay? Because you can have also, let's say, big span, okay, in it. and I want to predict actually the next location, right? So let's start from a study by Marta Gonzalez, which is a professor at Berkeley right now, and also by some, but there are many actually studies showing that human mobility is actually predictable. Okay, and in particular, this paper here is actually saying that mobility is highly recurrent. Okay, in the sense that if I take a data set, I can simply take some motifs, okay, of the network that I have, and I can try and I can predict, let's say, a fair amount of next location and mobility traces eventually. Okay, but so while this is cool, if you do things traditionally, okay, on the other side, if you're training a model on such data, that can be a machine learning model, but even a deep learning model whatsoever, you may have a problem, and so the models may overfit such information. Because I mean, if you repeat every single time the same entries, okay, and you do not have nothing model, the idea, let's say, starting from how the backpropagation, so the algorithm that are used to learn, okay, in deep learning models, basically they must overfit. Okay, so first thing first, we have to understand whether this assumption is actually there in the data. And so we try to define some overlap metrics, okay? So some ways, if I split randomly and according to what is done basically in the literature in the past 7-8 years for deep learning, okay? If I split the data set in train and test, okay, I want to measure how many traces that I have in the test set, okay, have any kind of overlap, so similarity, with the one in the training set. So we use such metrics to measure different things. So let's start with the longest, with the Jaccard similarity, sorry. So the Jaccard similarity is basically, I take two sets, okay, of variables, and regardless the order of the location, so regardless the temporal aspect, okay, of the trajectory. So suppose that das number are location ID, okay. It's like you say that your home is location number 1, if is here is location number 2, and then the restaurant, I don't know, a restaurant here in the city is, the restaurant is the number 3, okay, and you can have such trajectories here, okay. So here, regardless the order of the locations, without considering the temporal aspects, basically we are counting how many, in percentage, of course, how many times the numbers that I have here. So for each trajectory, this is kind of a problem when you have many trajectories, to be honest, because I mean, computing everything for all the pairs is kind of complicated. So you have to leave a server right there for a couple of hours, and basically, so with the Jaccard similarity, we simply want to understand the overlap. Okay, so how many items? Those are sets. Okay, so repetition also do not count. How many items here are in common with how many items of such trajectories that they have in the test set? And so basically, yeah. Then you have the longest common subsequence, and here what we want to measure if eventually to have well, here is sub trajectory, but it's basically the same of subsequences. Okay. So here we want to understand how many, let's say, consecutive points here. So with a temporal dimension overlap with consecutive points here. And this measure actually a different kind of overlap, because here there is the temporal component involved, okay? And then maybe what you want to understand is if the deep learning techniques are actually memorizing just the last location that I visit. So basically the importance of having this file here instead of having it at the very first position. And so what we have done is basically taking also this overlap from end, that is basically the longest common subsequence, but forcing that it may start from the end. Meaning that, for example, this 9 here, okay, supposed to have this 9 here as the end of this test set, okay? So you just have an overlap with this trace here, okay? So it's like that the last number of such a trajectory must be a 9, okay, to have an overlap. You cannot just have a 9, for example, here, okay? Because it makes no sense. So we just want to take everything from the end to understand the importance of having, let's say, recent location as a potential proxy for a prediction. And so what we have is that we took all the most widely used data sets for next location prediction, okay, that are this data set here. So the three that you see here, the first three are social media data, okay. So check-ins in places, okay. And here, indeed, you have taxi trajectory, so something that is more dense, okay. And again, here in the first three, you're working with IDs of location, okay. Well, here you're working with GPS or latitude and longitude points. Well, okay, and as you can see, so here the colors and the agenda say that the bars are the numbers of trajectory in the test set, okay, that has this bin of percentage of overlap, okay. So the first bar, for example, contained the number of trajectory with a 0 to 20% overlap with respect to the train set, okay, and so on. And as you can see, we have many, especially, so we have two behaviors, okay. There are the check-in data set that actually behave in this way. So there is this decay if we measure it with the Jacquard similarity, and also with the longest common subsequence with the most important bin, which is the 20–40%, okay. And it is a bit more heavy here with the overlap from end, okay. Well, here you can see that in Taxiporto something changes. So basically, we do not have that many 0–20 overlap trajectories, okay. But indeed, there are many 20–40 and so on. And we have the same behavior with the overlap from end here. So this is interesting because if we evaluate the model, so according to an accuracy, so how many times basically I predict the correct next location, and we divided the test sets according to such bins. I mean, as you can see here, so on the y-axis you have the accuracy, and and each point is a bin according to this line here, so to the x-axis. And as you can see, well, why in taxis we have, okay, good behaviors, but still the performances, of course, tend to augment while I go to the others. We have a huge problem with, so in the paper you can see all the data set, of course, but here we have a huge problem with those two examples, and all behave in the same way with the check-ins, okay? So with the check-ins, it is incredible. So basically, with the Foursquare, for example, there are deep learning models such as this one here, okay? So the orange line, that's almost reached the 0%, okay, with the 0–20 overlap, and they are great. So when we go on the 80–100%, so here basically, for example, in Foursquare New York City, if we measure the accuracy for the trajectories of 80 to 100 overlap, we are almost 100% of accuracy, which is great, okay. But then what happened that in the paper that you find around, you just see the average of such numbers, okay. So the average performance here, for example, of this model here, so the orange one for Gowalla is the 26% of accuracy. But I mean, it's not true. This is basically just memorizing, okay, what they already have. But so the question is, well, it makes sense actually, because I mean, if I do not have any information here, okay, so for such point, it is crazy to think that it may be able to predict actually the next location, because I just don't have observation, okay? And this is actually where we have to act if we want to create something that is geographically transferable. But so what we can do is actually push some mobility laws in the model, okay? So there are many mobility laws that do not really rely on let's say, they partially rely on geographical features, okay? So we can, for example, put in it, let's say, the distance law. So distance law is not the real name. I mean, the point is that we know that people usually travel short distances, okay? And there is also a metric called radius of gyration that can be used to actually try to understand how much actually a person travel, okay? And so, for example, if we take an individual trajectory, those are spatiotemporal points, so location ID, or because I mean, of course, every location ID then is also associated with a latitude and longitude. I mean, if I say I go to Ifisk, Ifisk is number one, I also can capture the latitude and longitude, of course. So we can easily compute the average and distance or whatsoever. So in the paper we use this one, but there are many distances you can use. Okay, between all the consecutive location and try to understand the average distance a user travel. Okay, so suppose that I'm in a location 1. Okay, so I'm here and I'm here for the first time. Okay, so I have no idea how the model can predict where I will go next, right? Because the model, so data never see me here in IFISC, okay? But if I tell to the model, well, okay, you are new here, but usually when you travel, you do like a 800-meter distance to go from a location to another. Okay, well, this may help, okay? And similarly with the vegetation law, so it's a very cool paper from MIT Sensible City Lab that is in natural human behavior or natural communication, I don't remember, that basically say that the visit to a location actually decrease as the inverse square of the product of their visiting frequently and travel distance, okay? And this can be computed actually. It can be computed by looking at the data set that can be associated to a single user or not, okay? But I mean, I do not need to put personal information about locations that I visited previously, okay, to gather such insights. And also, for example, the return and explorer dichotomy, then there are many laws, okay, that here are not considered and can be pushed in the paper. But here, for example, this is a dichotomy telling me whether a user, so a person, tend to visit always the same locations, okay, or tend to visit new locations. But okay, it is not, of course, associated to geography. But if I'm here for the first time, let's say, and suppose that you want to abstract that I am in a university right now, okay? Instead of giving exactly the first name. So you take like the category, for example, okay? So if you know something like this, and you know that usually after universities, after I visit a university, I always go to home, okay? Maybe you can say, okay, I'm a returner in that sense. So it is clear that once I exit the door, most likely I will go to the hotel, okay? Can also be the inverse. So maybe I can visit new location, and this can help. And if you combine, if you start to combine such things, so for example, I visit new locations, okay, and I do it in 800 meters, okay, from where I am right now. I mean, this can start to help the model and gain some insights, okay. And indeed, so what we do actually is, okay, here we have a model, okay, a human mobility model for individual mobility that takes input the old trajectories. So what such models do is basically a multi-class classification, meaning that they give, so they know that there are, for example, 100 points of interest around here, and they give a probability to each of them. And then they say, okay, you go to this, that is the one with the greatest probability, okay? So what we do is very simple. So this is the traditional model, and we operate there at the very end, okay? So at the moment, again, a simply fully connected neural network, so nothing mind-blowing, okay? That takes as input the probability of this model, okay? And at the same time, actually, the three mobility laws that I described before, but you can push whatever you want, okay? And the goal of this part here is actually the goal of a re-ranker, let's say, okay? So it takes the probability, it takes some additional information, and it tries to produce a new probability here, okay? Which is augmented with respect to the mobility law. And so we do it basically for all single probability item that we have here, okay, here in the middle. And then we have basically a new vector of probabilities and the new eventual next location. And actually, if we just stop on the 0-20 overlap, so here are all the trajectories that you see here have a 0-20 overlap, and these are the deep learning model, okay, on the x-axis, and on the y-axis we have the accuracy again. So as you can see, where the model was, let's say, going well, for example, with the taxi porto and let's say the longest common subsequent and so on, we do not have a relative improvement. So the blue bar here is the original accuracy, okay? And the red bar is actually the accuracy after we push in it the mobility load, okay? But as you can see, where we have problems, okay, so 2% is very low if you think about it, okay? But still, basically, we are more than doubling the results here, okay? So, and that's super interesting. So, for example, here we go from an 8% to a more than 15%, okay? In the Gowalla one, which is for many reasons the most difficult, let's say, one also. But as you can see, so first of all, we always have an improvement, okay? And we have a great improvement on the, so the greatest improvement is in the check-in data set, okay? Which are the most difficult one to predict. And this is great actually, but this is the first step toward the let's say the geographic transferability of the models. Because if you want to transfer something from a location to another, okay, then I have to work on the accuracies that are here, okay? I have to work on this location. Because I don't care about taking another trajectory in New York of things that I already see. So basically I'm here or in this, let's say 60 to 100 overlap, okay? Because it makes no sense to work there. I mean, there the models are working. And also another interesting thing is that, I mean, everyone is pushing deep learning, but actually the black line here is a Markov chain, okay? So, I mean, maybe deep learning is a bit of an hype. No, in the sense that there are things, okay, that must be do to, let's say, improve mobility models, okay, in any case. So, for example, there are data sets like Gowalla in which basically, if you do a standard preprocessing, the Markov chain is well above in many cases than the deep learning models, okay? But well, yeah, apart from that, we have to operate on such probabilities, and this is kind of an interesting result in that sense. Then, I mean, there are some limitations in this work, in the sense that, for example, we didn't choose many mobility laws. There are only 3 mobility laws, and I mean, we can do much more. And actually, the goal, so the great goal, starting from the mobility law, would also be to implement an embedding, okay? So an embedding is this thing, let's say, that takes variables and information and features that are in a space, in a certain place, okay? And with a function that can be learned actually, so with some parameter, put everything in another space with a lower dimension, okay? So maybe can be used to abstract also such information in some ways, okay? And this is the first step toward developing a positional embedding thing for encoder for spatiotemporal information. That would be great, because basically it's the building block for transformer that are this kind of neural network that, I mean, are going pretty well with both natural language processing and computer vision, but especially that are doing very, very well on transfer learning, basically. So they learn a task, okay? There is this positional embedding, and they produce the output, very well, let's say, output in terms of accuracy for another task. And this is great, but what's the point? The point is that if I have just a phrase, okay, so in natural language processing, doing positional embedding is kind of simple, okay, kind of intuitive. So basically, I have like a word, for example, if I want to do translation, okay, I have a word in English, and I can easily, more or less, associate it with another dictionary, okay. So basically, as a key, okay, with a word, for example, in Spanish, okay. This is not that simple with spatiotemporal information, because if I have, I don't know, a restaurant, for example, in Trento, where I work, it is not that simple to associate it with a restaurant, because positional encoding is basically a mapping, right, with things that happen, for example, in Trento, and now are happening here in Palma. And it is not that simple to actually map, for example, a restaurant that I visit there with one that I visit here. So there are many things that should be done in that sense, and so those are the 2 steps that, in my opinion, are necessary in some way. Okay. And so I think I think I'm done. If okay. Bye.
Thank you. Okay, thanks, Massimiliano. Okay, so we have questions here in the room, or later we pass it to online, or no?
Yeah. You just consider in the first part of the talk, you just consider the size of the city, no?
For the you mean for the transferability?
Mm-hmm.
No. So basically, we did not consider the size of the city. So to just make some sense out of the city selected, so there is just this economic document in the UK telling that the most 8 important ones are thus listed here. London was not included, so we put also London in it, but it's not about the size. I mean, okay. It's kind of a good proxy of the size, but yeah.
But I mean, within the city, just mobility in the city.
Yeah, so the flows are within the city, yeah.
Okay, so do you think it may change something if you change the course grain? Maybe if you go to city,
okay.
I mean, if you move in the city or in a quarter of the city or between city?
Okay, yeah, for sure, it's going to change. So that the main problem here is that we have actually more than 8,000 census tract in London, in the UK, okay, and we have a problem with we may start to have problem with memory, okay, also of the server, and that's what happened with us. So basically, if you take into account all the flows for training and all the flows for test, representing them in a matrix, okay. It's kind of problematic, so to fit them in the, let's say, in the memory. And indeed, so let me check. That's why actually, if you see here, we are working with tiles. So basically, everything that we have here are squares, okay. And so we take into account flows within such squares, so just within the squares, okay? And we use half of them for training and half of them for testing. So the testing unit, the train and testing unit is always the single flows, okay? But let's say separately. So we take into account also only, let's say, flows within a region and within another region. We train the model on it, and then we go to another region, okay? And we test everything. So that's the reason why.
Okay. The last question about the second part. Okay, if you consider single trajectories of individuals, but I mean, you show something that as a length that varies. So, like when you, for example, consider the Jaguar, the similarity, you show like trajectories that have different lengths.
Yeah.
So are you like how you are sampling the position of the individuals?
Okay. So you mean how we form the trajectories? So how we created the trajectory? Okay. Yeah. I mean that's basically following standard pre-processing techniques that are presented in the literature. So the most common one, for example, there are couples, but so this is another problem that is more in general of human mobility, so that there is not a real traditional way to sample the trajectories, right? So and that's very important because also the performances are let's say of course there is an impact of the processing on the. So here we are following the deep move technique. That is basically taking all the points within 2 weeks, so all the visit within 2 weeks, and that's a trajectory. Then basically I go ahead, and for another time windows of 2 weeks, those are the trajectories. So it may happen for some users that you have like, I don't know, when you start to use an app, you are on an app and you say, well, okay, I check in every day. So you have many points for in 2 weeks, okay, in the first 2 weeks. And then maybe you have just 5, 6 points, so check-ins, okay, visits to into the following 2 weeks, and so you have different length. Yeah.
Okay.
But there is definitely something that we should test. I mean, having different pre-processing and look at the same results that we show. I mean, that would make sense. I don't think that it would change that much the behavior. Okay, but something may change. Yeah.
Okay, thank you.
Thank you.
Okay, so more questions? The room? Oh, yeah.
Yes, it's more maybe to start a discussion about the comparison between the gravity model and the deep gravity model that you propose. Because I don't know, I feel that, okay, I mean, thank you for the presentation and for the work, it's very nice. But still, for me, it's not that impressive that you can increase the power of your model if you have more data or more local information. You know? Like your local estimate is better, but also you have much more information. No?
Yeah.
And the thing is, with the gravity model, is that you don't need to measure that. I mean, you don't have to feed the model with that many amount of things. And it's kind of universal. Maybe it's not that good, but it's universal. No? And in your opinion, is it possible to try to find better models, like, and to increase the power of a modification of the gravity model, or doesn't have any sense and it's better to work in your direction and do more deep learning things? Or what is your opinion on that?
Yeah, so let's say that. First of all, yeah, I totally agree with you with the gravity model and the difference. So here the point is not really on the performances that increase, but in my opinion are more on other two things. So the first one are the shape values plot here. So that basically for each single entry. So because let me check if I have the paper open here, because maybe it's more interesting to see also this one. So for each single entry, because you can also go from let's say this origin to this destination that are information you have to in the dataset. So for each single entry, you can actually try to understand what's going on here. Okay, and indeed this is weighted with the parameters. And the problem with the gravity model that you have is that you feed the parameter during the training. Okay. But such parameter, let's say that, I mean, if you go to an area to another that have similar characteristic, very similar characteristic, okay, you will always have the same parameters around the board, okay? This may not happen indeed when you go to deep learning techniques because there is no linearity, okay? And so that may be interesting. And also this part here of the explainability that, I mean, lack of it in the gravity model, okay? So that's, in my opinion, the two most interesting thing. Then, I mean, I also agree with you that most likely performance will increase if you go with other techniques, okay? Because, for example, so a fully connected linear layer is basically a linear regression, and then you put another function to add non-linearity, but you're doing nothing more, okay? There are more sophisticated techniques, so for example, convolutional neural networks, that if you are able to represent things as a matrix, and now there is also now for a graph neural network, for example, so you can also do not have a fixed square things, okay, where to work on. You can also definitely model the neighborhoods automatically, okay, because if you use graph neural network, for example, you have a points, okay, a node on the graph, you have connections. But if you measure a connection, for example, so origin and destination, okay, you are also able, sorry, to measure also the impact of the incoming edges of let's say both the origin and the destination. So, I mean, it makes sense that you can even improve such information. The point is that I do not personally really believe in, let's say, that it's worth working on things that just push the accuracy ahead, right? Because I mean, if you just work to augment an accuracy, I mean, you can, and definitely it makes sense, okay? And I mean, there are incredible works working in that direction. But if you're simply saying, okay, if I put a convolutional network instead of a fully connected layer in the model, okay, and you see, okay, well, the accuracy is higher. I mean, yeah, you can do it, but maybe it's more interesting to really find an impact and an application instead of pushing only to the accuracy. I don't know if I answered your question.
Yeah.
Oh, okay.
Yeah, thank you. But I thought that the whole point of these deep learning mechanisms was actually to increase the accuracy of predictions.
Oh, no, at all. At all. I think that, yeah, again, the two most interesting things are the explainability part and then let's say the differences in bidirection with the parameters.
I feel that somehow with this thing of the explainability, you also lose track of the physical. I don't know, like you are not you don't have like a physical postulate from which you extract a law. No, it's like.
So, okay, yeah, you mean that you're losing basically the origin idea of gravity?
Or of a law in general, no? Like how to translate this into an equation that you can use.
Oh, okay, no, I mean, no, you can't. I mean, taking this model and pushing it into an equation, I mean, eventually you can rewrite everything that the model is doing, because I mean, in the end, we just use linear layer and softmax. Softmax is a well-defined function, okay? And also linear layer as a well-defined function. So what's going on in my opinion is that when you do the back propagation, so when you fine-tune the parameter, when you fix the parameter of the equation, that's where a problem, let's say, may start with deep learning. But yeah, I mean, maybe you're losing something that, with respect to a law. I mean, you cannot generalize it with a law, definitely. Yeah.
Okay.
Yeah, that's right.
There is anybody online that has questions? If so, please unmute and we'll also just show the camera if you want. Okay.
Hi.
Yeah.
I have a question regarding the explainability. And the explainability and associated the fact you can apply the model to different places. At some point in this transparency, you show that population plays no role, practically is irrelevant for explaining the movement of people in England. Because it's very well down. I mean, it's the last one or the one before the last. Who cares about population? But then population plays an important role in other places.
Yeah, no, but I mean,
so then how you can envision exporting what you learn in England to another place if population, which turns out to be a key role in Italy, is not relevant for the model in England?
Okay. So I will try to answer your question. Please feel free to stop me if I'm not answering it. So I think that you're referring to this slide here, where basically we are saying that on the left there are things. Maybe, yeah, there are features that are ordered by importance. Okay, so here, by the way, I'm not saying that population is not important. Okay, I'm saying that there are things that in our case are more important than the population. Okay,
well, that's the same basically.
Yeah, that's more or less the same, because I mean, if we look at the population, well, let's say. Well, this box here that you can see in the middle is actually the focus of the point and their importance. Okay, and more or less are the same. So first thing first, population. I mean, is not that different with respect to the points above. Okay, but there is more. I mean, here we are training everything with the census data. Okay, so. It may be that we also have included a bias in the data themselves, okay? Because basically they are collecting how people commuting for work, so from home to work destination. So it may make sense that if I start to have many points in which people can go and actually work, they gain some importance over the population, right? So maybe that's maybe.
No, but my question is more than says on philosophical side, okay? So I mean, either population plays a key role or it does not play a key role. It might play a key role because the country, because the data, because whatever, or it might not because of the same things. But the point is that if it plays a key role, the data trained for models where it plays a key role probably will not work in places where it is not relevant, and the other way around. I mean, when you try to export this model from one place to the other, one would expect that something which is needed for the model to be exportable is that the issues that plays the major role in the model are the same.
Okay. Yeah, I think I'm not sure.
Well, let me put in a physical sense. I can export one model from one physical system to another one. But I would require to have the same variables in the same, which are the relevant ones.
But it's not about the question. It's just that I cannot really understand. What
okay. He says that he cannot understand the question, or
no, the question. Yeah, is that I mean, it's not that I can. I'm not sure I can hear correctly what you're saying.
Okay.
My fault. Yeah.
For the sound, that is not good. Okay. But can you repeat then?
Yeah. The point is that I would expect that for this data or this model to be exportable from one place to another place, that can be exported only to the places where the variables which are relevant are the same.
Okay, yeah, because if you have ranked the variables,
okay.
so he's saying that, okay, imagine that for England, the important variables are these ones. No? If you want to export the same model to another country, it should be a country that has the same kind of variables.
No. Okay, yeah, no, that's clear. Okay, now, sorry about that. Yeah. So it's actually part of this point here, I think. So basically, if we want to really actually transfer everything, so the next challenge is this country to country. I mean, doing it within a country is simple, okay? And I totally agree with you that if I want to take a model that is trained in the UK, for example, okay, or in London, and try to test it in Italy, so to go in another country, I mean, we may face such issues, right? Because the weight of the population, for example, that in England is not that relevant, is relevant in other countries. And that's why, indeed, it may be interesting to not only have the population and the points of interest, okay, but also try to introduce some more socio-demographic data that may help, not in, let's say, I mean, may make more easy the work, right? Because I'm not saying, okay, there is this population in the region and the destination.
So your idea is, so let me rephrase that. Your idea is that to make the model to be exportable, to introduce new variables, add more data, which would tell you what are the relevant variables of the ones that you have in each country. So this cultural data might tell you whether population is relevant or not. I guess that's the idea, no?
Yeah. Correct.
So you could classify the countries according to the variables that are needed, and then you could have like a kind of class of universality, no? For the
yeah. You can definitely do also something like that, okay? But I mean, that's cool. It may not be that easy, right? Because we may have extremely different countries still. But I mean,
there is also the other question that is tricky. That is, these variables are not fully independent. It's not that.
No.
Population.
No.
They are correlated. So sometimes population may be down in the scale just because the information is inside the other one.
Yeah. Sure.
So, but yeah, I mean, the idea is that there could be actually some classification of the countries.
Definitely. Yeah.
Okay. Thank you.
Yeah, thank you. And sorry about
anybody else online? No? Okay, so well then let's stop here because otherwise we can continue. He will be still around a few days. So okay, if you want anybody to talk to him, he will be available upstairs. Okay, so thanks everybody, and then we close the seminar here. Se acabó. Sí, vale.